Okay, we're going to start 12.6, which is all about surfaces in R3. We've already seen a couple of examples of this. One example is that of the sphere, or the surface of the sphere. And the general equation for that is the following, where our center of the sphere, in this case, is ABC, and the radius is R. And just a slight extension of that is what's called the ellipsoid. So let's do just a direct example here. So example, then I'll write the general equation. Let's say we have x squared plus 2, oops, sorry, 4y squared plus 16z squared is equal to 64. Then this, when we divide both sides by 64, we get x squared over 64 plus y squared over 16 plus z squared over 4 is equal to 1. And this is the generalization of an ellipse. Just like a circle generalizes to an ellipse, a sphere generalizes to the ellipsoid. So here our center point is 0, 0, 0, because we have x minus 0 squared. You can think of these as x minus 0 squared over 64 plus y minus 0 squared over 16, so on and so forth. Y minus 0 squared over 4 is equal to 1. And the stretching that's going to happen, the stretches, well, we're going to have 8 units away in the x direction, both the positive and the negative direction. We're going to have 4 units in the y direction and 2 units in the z direction. So let me first draw the ellipse overall, and then I'll label the points. So what we're going to have is something like this. Where our axes are given something like this. So this is the y, this is our x. So this point right here, for example, would be the point 8, 0, 0. And this point right here would be the point 0, 4, 0. This point on the other side would be the point 0, negative 4, 0. This point would be the point 0, 0, 2. And somewhere down below here, we would have the point 0, 0, minus 2. So on and so forth. This point would be negative 8, 0, 0. Okay? So this is what's called an ellipsoid. So from the center point, you simply go out as many directions as required. So the general form here, let me just write that. General form is x minus a squared over d squared plus y minus b squared over e squared plus z minus c squared over f squared is equal to 1. This is the general form of the ellipsoid, sorry. So that's just a generalization of the sphere. Another one that we have seen already is the equation of a plane. And these are of the form ax plus by plus cz is equal to d. And we obviously have the normal vector here of abc. Just to be complete, let's do at least one example of graphing an equation of a plane. And usually the simplest way to do it is to plot all x z-intercepts. Of course, they're not always going to be in existence. If the plane is parallel to the xz plane or parallel to the yz plane or something like that, then you won't have every intercept, but a lot of the planes do have all intercepts if they're slanted. So let's compute the intercepts. If you set y and z to be 0, you get x equals 1, so you get the point 1, 0, 0. If you set x and z to be 0, you get y as minus 1. And if you set x and y to be 0, you get z as 1. So you get the points 0, negative 1, 0 here, 0, 0, 1 here. And we can plot the graph as follows. I'll plot the graph in red. So we have 1, 0, 0, 0, negative 1, 0, and 0, 0, 1. And so we can just draw, if you will, the triangle portion of the plane. Of course, it's not limited to the triangle. The full plane will be, so we'll be extending that triangle off to infinity. So the full plane is extend the triangle off to infinity in all directions. Okay, but those 3 points, as you recall, 3 points defines a unique plane. So that's the second class of surfaces. Another class of surfaces is either circular or elliptical. I'll put that in parentheses, but essentially they are cylinders. So let's do a quick example. We've also actually seen one of these. So let's take, let's say x squared plus z squared is equal to 4. So that in the xz plane, we have essentially just a circle. So here's x, here's z. And our graph would just be a circle in this plane, where the y-axis is stretching out in this direction. And since y is free, this just extends out to an infinite cylinder in the y direction. Let me just adjust this end circle right here. So it'd have something like, and then in the back it would be kind of dotted because that's usually in the back. So this is a surface again that we have seen already. It's, I think, in one of the first sections we saw something similar to this in chapter 12. You can also have a situation where the cross sections here are ellipses. I'll leave that as one of the exercises at the end. Let's go to another class here of graphs. This one is somewhat new. This is called a parabolic cylinder. Now here, by the way, the term cylinder really just means, what is the definition of a cylinder? It just means the surface consists of repeated copies of the same curve. Copies of the same curve. So for example, in the circular one here above, it's a cylinder because every cross section is this same circle. It's sort of the classic cylinder, if you will. Parabolic cylinder, so for example, if you have z equals y squared plus 1, then we can graph first in just a zy plane, z equals y squared plus 1, which is just a parabola. And then we can extend that out in the x direction because x is free. So x is a free variable. So we repeat this graph for every single x value. So get something like this, where the repeat everywhere you go, this graph is repeating. So it's a cylinder in the sense that the parabola is repeating over and over and over. So that's an example of a parabolic cylinder. Let's do one last one here before we pause on this video. This is a cone. So this one is just a bit more involved than the other one. So what I'm going to do for this one is I'm going to use what are called trace curves to draw the surface. And we're going to do these trace curves in two ways. First, we're going to draw all the trace curves just in the xy plane. Once we draw them all in the xy plane, I'm going to sort of, in a way, lift them to the 3D space. And then we'll be able to kind of see what really is going on. So let's start here with, we'll call this part A, call this part B. What I'm going to draw trace curves is essentially, the method is to fix one variable. Fix one variable as a particular value and see what you get. And what we're going to do is we're going to fix various z values to start with. So let's start with z. So let me put a little table here, put the equation, and then we'll put the plot in a second. So let's start with z equals 0. We'll do 1, -1, 2, and -2. Oops, -2. Okay, so our original equation was z squared is x squared plus y squared. So that our first equation here is 0 is equal to x squared plus y squared, which means that x and y themselves have to be 0 because, well, x squared is always positive, so is y squared. The only way that happens is if x and y are 0. Here we have x squared plus y squared is equal to 1. Here also we have x squared plus y squared equaling 1. And for these both, we have x squared plus y squared equals 4, because z squared is 4 in that case. So how do we draw the trace curves? Well, let's draw them again just in the xy plane for now. What do we have? Well, we have the point here. Let me draw them in red here. We have the point 0, 0, 0, which is the trace curve of the first when z equals 0. For z equals plus or minus 1, we have a circle of radius 1. And again, this is all happening just in the xy plane for the moment. Once we change the value of z, we get z equals plus or minus 2. We get a circle of radius 2, and that corresponds to plus and minus 2. Now let's go ahead now and lift these to the three-dimensional space. What do we mean by lifting? What we mean by lifting is that, well, we're going to start off with the point 0, 0, 0 from the first guy right here. And then we're going to say, okay, well, at the plane z equals 1, so here's the plane z equals 1, we're going to draw that same circle. So the circle of radius 1 gets lifted to the plane z equals 1. Similarly, for z equals minus 1, which is somewhere down here, we also have a circle of radius 1. Let me draw that a little better here. So we have the same circle at -1. Now we do the same thing at z equals 2. We say, okay, well, if we go up to 2, we have a larger circle. If we go down to -2, we also have the same larger circle. Now, how does this actually become the cone? Well, let's fix one last variable. Let's set x to be 0 in our equation to get z squared is y squared, or z equals plus or minus the square root of y squared, or z equals plus or minus the absolute value of y. Well, if you draw the absolute value function in the zy, this is when x is 0, you'll get something like this. So that's one absolute value function, and then there's the other absolute value function. And now you can see the cone forming. So overall, in one go, if you had to draw this, it would just be, here's the the part of the cone that points upward. There's also the part of the cone that is pointing downward. And then there is your coordinate system, which lives here. Okay, this is the graph of z squared is equal to x squared plus y squared. Okay, by the way, this is also plus or minus the square root of x squared plus y squared. So the positive square root of x squared plus y squared is just this top cone, and the bottom cone is the negative square root of x squared plus y squared. That's also an important fact that comes in handy. We'll conclude this video with an exercise, which is to graph the following. So x squared is 4y squared plus 9z squared, and also y equals 4 minus 2z squared. Okay, so in the next video we'll start off with these exercises. There are probably another 3 or 4 categories of graphs that are left over, and we'll do those as well in the next video.